So this question, we have block X traveling toward block Y, which is initially at rest. So we have a V0 equal to 0 for that one. They collide together, which describes the final velocities after the collision if the collision is elastic. And so elastic right away means the kinetic energy is conserved. So we look at the first choice that we have. Let's approach this conceptually first. Let's look at the first choice. And the first choice, we look at that and we see this is a sticky collision, which we generally associate with inelastic. Second one is a bouncy, which can be elastic. Third one is bouncy. And the fourth one is bouncy. So right off the bat, it looks like we're going to eliminate choice A because the kinetic energy is not conserved. So in all of these interactions, there are two things that are going to happen. We need to look at our two lenses. We have our momentum lens, and we have our kinetic energy lens. We know that P0 is going to equal P, and so let's take a look at that. The initial momentum in this case comes from one of the particles, and P0 is mv, and we have 2 times 4, so the initial momentum is 8 kilogram meters per second. So now we can just test each of these cases to see if they have a momentum of 8 kilogram meters per second. So in choice B, we have mv plus mv, and we have a mass of 2 times 1.8, and a mass of 1/2 times 5.6, and that is 3.6 plus 2.8, which is 6.4. So we can rule this one out right away because the momentum is not conserved. We've shown that. Choice C, again, we have two particles, mv plus mv. And so we have 2 times 2.4 plus 1/2 times 6.4. So 4.8 plus 3.2 is 8. It looks like, at least in terms of the momentum, we have possibility of choice C. And now we'll look at choice D. We have mv plus mv. 2 times minus 0.8. And the other one is 1/2 times 19.2. So that's minus 1.6 plus 9.6, which gives us 8.0. So it looks like in both of these cases, C and D, the momentum is conserved. So now let's look at the kinetic energies to see if they're conserved. We'll just start with D. We're going to start with our initial kinetic energy, which is 1/2. Initial is going to be the final kinetic energy. 1/2 mv squared, and we have 1/2 of 2 times 4 squared. So that gives us 16 joules. So every one of these cases should have 16 joules. So then we have 1/2 mv squared plus 1/2 mv squared. 1/2 of m in this case is 2 times 0.8, negative 0.8 squared, plus 1/2 of 1/2 times 19.2 squared. Well, these cancel, and we're left with 0.64 joules, and 1/4 plus 1/4 of 19.2 squared, which is 305.64. A quarter of 305.64 is 76.4. So clearly we can see we have way more than, it's much greater than 16 joules. So in this case, we have created kinetic energy. It's not a closed system at that point. And so choice D is out. So kinetic energy increases. Not only is it not conserved, it increases. If anything, we would expect it to be lost. So it's a closed system in that case. And if we try choice C, we have 1/2 mv squared plus 1/2 mv squared. And so that's a 1/2 2 times 2.4 squared plus 1/2 of 1/2 times 6.4 squared. So 2.4 squared is 5.76. And that gives us 1/4 of 40.96. And that then gives us 10.24 plus 5.76 is 16. So we see that that's the case. We have 16 joules and 8 kilogram meters per second. So we are clearly showing that choice C is the best answer in this case. And if we look at choice A, we find out that if we were to go through and do the calculation, that this works out to be about 12 joules. So again, in this case, the kinetic energy is not conserved as we expect. And so we could just apply those two perspectives and find the best answer, choice C.